A very good afternoon to all dignitaries, guests, and delegates. It's Yokta Sharma, and I feel privileged to extend my warm welcome to all presented here. And let me tell you that today's session will be chaired by Dr. Anuvedita Singh ma'am from Israel. Welcome, ma'am.
Thank you so much. Okay, so should we start now?
Yes, ma'am.
Today's first speaker is Professor Chanpeng Li. Currently, he's working at the Department of Mathematics in Shanghai University, China. And his current research is focused on numerical methods and scientific computations of fractional partial differential equations. He serves editor-in-chief and associate editor post of various reputed journals. And he has also written a book entitled Numerical Methods for Fractional Calculus. He has published more than 100 papers and has more than 36,000 citations. It's really a good number. It's impossible to be mentioned his every single accomplishment because there are a lot. So his achievements have been recognized by many different awards, including Shanghai Natural Science Prize, Bao Steel Prize, etc. So, however, today we are here to be benefited by Professor Lee's outstanding talk. But before just overing this session to Professor Lee's, I want to say something to you all. Okay, see, we are here to hear Professor Lee. So I just want everyone, if you are here and if you are giving some time to this talk, so be present here and be full benefited. Okay. Professor Lee, it's a warm. I think is there any?
Yes, ma'am.
Yes. So, is there any problem or what?
I think is there some technical issue, Professor Lee? Am I audible?
I think it's we can write. Okay. Mm. So what's the solution?
I think.
Yes, I think he's trying to fix his mic. Okay, let's wait. Just unmute him.
I can't unmute him. Actually, I can't unmute him. Yeah.
Okay, can you hear me?
Yeah.
Thank you so much.
Thank you. Okay. So I'm sorry. I'm sorry.
It's okay. It's a technical issue, so it's okay.
Anuvedita, I would like to request you kindly once again introduce Professor Lee and proceed the lecture.
Is it okay?
Yeah.
Yes, this is fine.
Okay, thank you. Okay. just report our recent work in respect of fractional differential equations. Is since this Monday I got COVID-19, now I'm recurring. So I feel sorry about this. Okay. Now I present forward for this talk. T, where solution to some problems are algebraically asymptotical. Okay, just like this. So there is one question: does there exist that the solution of some problems are logarithmically asymptotical? From the physical phenomenon observed and references available, Adama function calculus is suitable for describing logarithmic asymptotics, like the Leibniz logarithmic Grip-Null of with coinelastic materials. This is three papers. And now we present the title of the talk. Discrete formula for Kappa-Adama fractional derivatives. 自强理. Okay. The outline is organized as follows. We first give an introduction, then we examples are also displayed to show the effectiveness of the formulas. Then we use the what is fractional? What is Adama fractional calculus? To mention derivative, then integral, but in fractional calculus, we often mention in integral first, then derivative. Definition of Adama fractional integral. Here, minus means integral, since alpha is part. This is the column log t minus log tau. This alpha is 1, but here there is d tau over tau. Okay. Since we use a logarithmic operation, we require a is positive. If ft has a is positive, in the above definition, the condition ft in L1 is presumed. In some situations, such a condition from the integral, then delta derivative. This is the integral first, then delta derivative. Okay, what is delta? Delta is also a Seidel operator, t over t and delta n, like this. Okay. For the derivative definition, we need the condition ft in this in the Adama fractional calculus. Then integral. If these values exist, equality, once we get the we know there are lots of numerical methods for the capital derivatives, but there are few. This, okay. This report mainly comes from here. A is the starting time, T is the end point. So we need give a partition for the interval. This tk t0 get top. This is the top. Okay, so this is the uniform be a fixed population function of t. A plus sigma is sub-interval over the tk over the interval tk plus 1. We use the point. Okay, sigma is sigma is less than 1. Is less than 1. Okay, the linear interpolation. This is truncation error for the L1. Okay. By some calculations, we can get this as a formula. Okay. Now we derive the L1 to 1 sigma formula for the Kappa-Dama derivative at this point. So it's different now at this point. Okay. In this subintervals, we use the quadratic interpolation function. But in the by this interval, we use the linear function. This is error. We can get this is the coefficient. So we now we can get the truncation. It is 3 mass alpha, almost 3 mass alpha. Okay. Now we get the theorem for any order alpha. The coefficients CJK alpha sigma defined in the equation 2.2165. These all of them are positive. Okay, and they have the following property. The above for the order in the interval 0, 1. What about the case for the interval 1, 2? Now with the H2, N2 formula. This is the midpoint of the TK minus 1 and the TK. This is just arithmetic mean of a TK minus 1 and TK. We show the quadratic ammeter interpolation H log 2, 0 ft. This is here 0 is the T0. Okay. 2 is a quadratic. Okay. like this. This is truncation error. In the rest interval, tk minus 1 over 2 tj plus 1 over 2, we use 3 points tj minus 1, tj plus 1. It is obvious that the tj minus 1, tj plus 1 are outside of the interval. Okay. We get this Newton interpolation. And this is a truncation error. Now we get the derivative value at the point tk minus 1 over 2. That in this interval, we use the Hermite interpolation. In the rest intervals, we use the Newton interpolation. And this is the truncation. Okay. We get this is the error. Truncated error. This is 3 minus alpha, as also the 3 minus alpha. Okay. We can also get the properties of the coefficients ckk alpha in the formula. Ckk alpha positive and ckk alpha negative. We also have following properties. While we discuss the positivities of the coefficients and the velocities of the coefficients, since we may use these conditions when we discuss this numerical stability. It's a special non-uniform partition. That is just change the capital model. In another case, something like the capital derivative. Okay, we skip this. Now, let's give numerical examples for the discrete formula in about in about formulas. The capital derivative, capital derivative. Okay, this is starting time 1 and endpoint time endpoint 2. This is the initial value u equals 0 and gt like this. We get the exact solution like this. We use the L1 2 formula. This is the type A. This is type B. We just gave the type B case. Why? In our paper, we also mentioned that the capital derivative can be changed into the capital derivative. We show which uh, which type formula are better. For the type I, for the type A, this is the convergent rate. This is the convergent rate. It's almost the same. The convergent, but for alpha equals 0, type A seems to be better. Seems better. For alpha, it means that for alpha, for the alpha equal to 0 point is better. The type A is better. It means that from alpha, if alpha is positive, is equal to or bigger than 1/2, type A formulas better. This is for L12 formula. Okay. We use a L12 sigma formula. For the type A, this is for the type B is better. But for this type B seems better. But for the in this case, type A, type B has the same result, almost the same result. Okay. We discuss we need to compare the result H2 and 2. Okay. We use a type A, type B, H2. From this table, you can see type A is better. This rate you can see. It was type A is better. Okay. You can see type A is better. Now we use the formula to the Lorentz system with capital Adama fractional derivative. This is Lorentz derivative, but the Lorentz system, but the derivative are in the sense of capital Adama case. How to detect the appearance of a chaotic attractor? We need to compute the leading Neapolovitch point. If the leading is Neapolovitch point positive, then the chaos is then there is a chaotic attractor. It's from this. This is alpha. Okay, you can see alpha 1, alpha equal to 0, 1, line 5. There's a chaos, so chaotic. But this is no chaos. Okay. Now we use the formula to the BT system. This is the BT model. We can get the result by using the H2N2 formula. Now we present some references. This paper is for L2 minus 1 sigma for the capital derivative with order in this interval. This is L1, 2. for capital derivative with order in this interval. In this paper, L1A for capital automatic derivatives with interval in this interval. This is a PhD thesis. He's my PhD student. Okay. Non-uniform L12B for the capital automatic derivative with order in this interval. And this is a non-uniform L1B for the capital automatic derivative in this interval. In this paper, this is for capital derivative. The talk comes from these references. In this paper, L1A, L1B, L21A, L21B for capital automatic derivative are reported in the appendix part. There are some scholar papers, some papers from, there are some other papers from other colleagues. Okay, there's Yan and Wang and Peng and so on. Thank you all for your attention. Okay, thank you.
Yes, thank you, Professor Lee. Now the session is open for questions. So, Mr. Deepak Tiwari, he raised his hand. Can you unmute yourself and ask question? Is it possible for you, Deepak? Okay, Atul, Mr. Atul Kumar, you can ask.
Professor, hello,
Yes.
Professor Shankly.
Yes.
Have you ever worked with delay for this kind of problem?
Sorry?
Have you ever worked with such problem for delay differential equation?
You mean the condition of the definition?
No. Have you ever worked with this kind of method for delay differential equation?
I cannot catch your idea. I introduced the capital automatic
differential equation. Okay. Sir, I have a question.
If you have, I can send my TPT to Rahul. Okay. If you have any question, you can email me.
Okay, sir. Okay.
Okay, so it was a great talk. Thank you so much for your valuable time, and please take care of yourself. Thank you so much. Okay, so the thing is, if anyone has any query, okay, so you can write to him and he will respond you. Okay. So Rahul, should we move for next presentation?
Yeah, definitely.
Okay. So the next talk is Dr. Saraswati Saha. Saraswati, are you here?
Yeah, I can hear you. Yeah, I am here from the last meeting.
Ah, great. Oh, great to see you after
Yeah,
after a long. Okay, so let me introduce her first. So Dr. Saraswati Shaha, she has completed her PhD from University of Delhi, and now she is a postdoctoral fellow in National Autonomous University of Mexico. Okay, so yeah, over to you, Saraswati. We are
yeah.
here.
Thanks, Anu. Thanks for your kind introduction.
Yeah, you're welcome.
This is my second lecture, so I
Ah,
think,
I'm so
yeah,
sorry. I was not there. I'm
yeah.
so
So
sorry.
I think participants
But
are aware
then,
of the things.
yes.
So in the last meeting, firstly, I would like to recall the last meeting, what we discussed and what I will today discuss. So in the last meeting, we discussed about the classification of first order PD, and then we go through the solution of a very basic first order PD one can think of, a very basic first order PD one can think of. So down after a finite length of time. So I think everyone have gotten the PPT, and also everyone has gotten the notes of the same. I shared with Dr. Rahul. So if you guys have any doubts from the previous classes, then you can ask to me.
Say with everyone, please ask questions. See, this is for you all. Okay. And if you are giving your time, so please be sure after this minute or this hour, what did you get? Okay. So please ask questions. There is
Yeah.
no kind of silly thing, nothing. Whatever you want to ask about this session, about this presentation, you can ask. Okay. So please.
Thanks, Anu. Actually, I just wanted to say this thing because I think students don't students don't pay that much attention. I think only 50% of them pay that much attention.
Yeah, it's okay, but yes, if you are giving your time, then please value for it. Okay.
Dr. Rahul will share the PPT. Don't worry about that. I have already sent him yesterday. I sent him, and he will send to all the PPT. I think I was going to take another lecture, so he haven't share. So please tell me which kind of PD this is. Which kind of PD this is? Please recall the definition. Which kind of PD this is? Is it linear or semi-linear or quasi-linear? Can anyone tell me which kind of PD this is? Okay, so let's have a look at the definition of the Cauchy-linear and semi-linear PD. Here, the highest order derivative, yeah, Cauchy linear, not it is Cauchy linear. Okay, so the highest order derivative is linear, and their coefficients are function of x, y, u. That is the highest order derivative is linear, but it is non-linear in its unknown variable. It is non-linear in its unknown variable. So it is a Cauchy linear PD. Yesterday we discussed the linear PD, and today we are going to discuss the Cauchy linear PD. And if we are given a smooth initial data, then it is known as Cauchy problem. A Cauchy linear PD with a smooth initial data is known as Cauchy problem. So what kind of solution it had? The solution of this PD will be of like this. And this is a surface in solution space. So the solution of this PD will be surface in a solution space. So can we write it like this? Yeah. So we can write it like this. If you recall, so what solution I got? I got the solution u naught x minus c naught t. And so I can also write it like f x t u equals to u minus u naught x minus c naught t. So I just written in this form. And what will be the gradient of the function f? What will be the gradient on that surface? So just keep this thing in mind. Now recall this. We can write a comma b and c dot ux ui minus 1 equals to 0. So I think everyone is aware of the dot product of the two vectors. If this is one vector v1 and if this is another vector v2, then the dot product of two vectors is defined as v1 dot v2. It means this v1 and v2, that is angle between them is 90 degree, that is this v1 and v2 are perpendicular to each other. So what does it imply? It implies that this vector ABC will be perpendicular to this vector, and we know that this is the gradient of f. This is the gradient of f which denotes the perpendicular on the solution space. It means that this vector will lie in the tangent plane of the solution space. If this vector is perpendicular on the solution space, then this vector will lie in the tangent plane of the solution space. So A, B, C will lie in tangent plane of the solution space. Okay, so when this vector lie in the tangent S and U is also function of US, and consider a point vector R that is written by XYU. So what will be the total derivative of R with respect to S? It will be dx upon ds, dy upon ds, and du upon ds. And everyone know that the total derivative basically represents the tangent along that independent variable in this direction. So this is the tangent along x and tangent along y and tangent. And we are also given a condition u x comma y x equals to u not x. So this is the initial condition. Suppose this is the gamma curve from which this point pass u x comma y x equals to u naught x. If we take y equals to 0, then simply we can write ux comma 0, but I am taking a generalized initial condition so that you can relate these things. So if you consider the point x, y, u and you trace the curve, if you consider the point x, y, u and you trace the curve, so basically it represents tangent passing through the solution point, and as well as it represents the characteristic. It will represent the characteristic. And if we recall the yesterday point, then we know that every characteristic will pass through the initial condition. Every characteristic will pass through the initial conditions. It means each of these characteristic will pass through gamma. So S is varying along these, and this is the initial condition. Suppose I am taking x equals to xi, so xi is varying along this. You can simply write initial curve as x equals to xi, and consequently y will become start and will start to emanate along these, because every characteristic line will pass through this initial curve. So how we will find the solution of the system? How we will find the solution of the system? The solution of the system can be found by solving this system of OD with this initial condition. By solving this system of OD with this initial condition. And as soon as we will be able to solve this system of OD with this initial condition, we can write the solution U in terms of X and Y. Now, the question is how to solve this system of ODE, whether we will get a unique solution or not. So if we recall the existence and uniqueness theorem of the system of ODE, if we recall the existence and uniqueness theorem of system of ODE, then We will get a unique solution only when A, B, C are nice function. If A, B, C are smooth function, and if we will be able to derive the solution, then solution will be written in the form x equals to x s comma xi, because initial condition is in xi, y equals to y s comma xi, u equals to u s comma xi. Now the question is that s is a parameter and xi is an initial condition. So how we will write u in the terms of x and y? It is only possible if we are able to write s comma xi in the terms of x and y from these two equations, and then we will be able to write u in the terms of x and y. So please tell me, is it possible every time to write x comma y in the terms of s comma u in the terms of x comma y? If x, that is a function of s comma xi, y is a function of s comma xi, so basically x, y to s comma xi coordinates. So from here I am able to write this. Is it every time possible to write this? Is it every time possible? A one function. And what is the condition of one function? The Jacobian of this is a non-zero quantity. So what will be the Jacobian of this? This is a non-zero quantity. And in fact, if we talk about in the neighborhood of this, we are not going long far away from this gamma. If we are talking in the neighborhood of this xi, and we are able to write the solution in this neighborhood, then it is enough for us. So basically we can write j 0 comma xi. This should be equals to a non-zero quantity. And with that, we can also say that along this curve gamma, this equation gamma is p, and p is the point xi comma 0 comma xi, because we are taking s comma xi, so 0 comma xi. So just write a at p ux, b at curve p uy equals to c at p. And since our initial condition is u x y x equals to u naught x, or simply I can take xi at along p. So u xi y xi dy over d xi, and the right hand side will be u naught s xi. So you can simply write it x xi ux plus y xi uy equals to u naught dash xi. Okay. So we need to find out the value of ux and ui. The value of ux and ui, we need to find out the value of two dependent variables, and we are given two equations. So we need to find out the value of two variables with the two algebraic equation, and that is a non-homogeneous algebraic equation. So what will be the condition? If you recall the linear algebra, so what will be the condition? It will have a unique solution if the coefficient matrix, just write this because this equation is same. So these two equation, the coefficient matrix A at P, B at P, and then x xi, y xi, C at P, and u naught dash xi. And if you keep in mind, then A at P and B at P is nothing but dx over ds and dy over ds. So this coefficient matrix is nothing but this Jacobian. So this algebraic equation has a unique solution if the determinant of this coefficient matrix is non-zero. And what will happen if the determinant of this coefficient matrix is 0? Then whether we will get a solution or not. If the determinant of this matrix is non-zero, then we will get a unique solution. And what will happen if the determinant of this matrix is 0? Can anyone tell me, recalling the linear algebra, can anyone tell me what will happen if the determinant of this matrix becomes 0? Whether we will get unique solution or not? Infinite, okay. And either we will be getting infinite solution. Yeah, exactly. Either we will be getting an infinite solution, either infinite matrix becomes 2. If the determinant is, if suppose this matrix is A and the determinant A is 0, then rank can be 1 or rank components are not equals to 0. So obviously rank will be 1. So if the rank of this augmented matrix, is equals to T is equals to 2, then it is violating the condition. It is violating the condition, and in that case we will be getting no solution. Rank of, suppose this is A matrix and this is B. Rank of augmented matrix is equals to 2 and rank of A is 1. In that case we will be getting no solution. And if rank of this augmented matrix becomes 1 when rank of A equals to 1, in that case we will be getting infinite solution. In that case we will be getting infinite solution. So next we will go through an example just to have a look how we are getting infinite solution, and we will also see a geometric representation of this example. So can anyone tell me which kind of PD this is? Semi-linear, quasi-linear, or linear, or fully non-linear? Which kind of PD this is? In which category it falls? No, not quasi-linear. Yeah, it is linear, because you can say that it is linear in its highest order derivative and it is also linear in U. So this is a linear PD. But this is not that much simple as we discussed yesterday. So, and the initial condition is given U x comma x cube equals to 1. So this is the initial condition. Basically y of x equals to x cube. So what will be our dx over ds? 1. We can see a equals to 1 here. Dx over ds is 1. Similarly, dy over ds is 3x square and du over ds is 1. Initial gamma curve, it is x equals to xi, y equals to xi cube, and u equals to u naught xi, that is equals to 1 at s equals to 0. So what will be our Jacobian matrix? So firstly, we will solve this to find out the form of x. Okay. So after integrating this, I will be getting x equals to s plus constant. So firstly, we will find the value of x, y, u, and then we'll see whether we are getting the unique solution or infinite solution or no solution by having a look at the Jacobian matrix. So from this equation, I am getting x equals to s plus constant, and the initial condition is s equals to 0. Yeah, du over ds, du upon ds is 1. Because c is 1 now. What was the equation? A del u over del x plus b del u over del y equals to c. So c is 1 here. That's why I am writing del u over del s equals to 1. And b b is 3x squared. That's why I'm writing dy over ds equals to 3x squared and dx over ds equals to 1. So dy upon ds equals to 3x squared. So I need to keep the value of x. I need to put the value of x from this equation to integrate this equation. So it will be 3s plus xi square, and on integration it gives y equals to s plus xi q plus constant. And what is the initial condition? Initial condition says that at s equals to 0, y equals to xi cube. So what will be the constant? It is xi cube, it is xi cube. So the constant will be 0 and simply y becomes s plus xi cube. And from du over ds I will be getting u equals to s plus constant, and again at s equals to 0, del x over del xi, 3 xi I will keep, and del x over del s. So del x over del s is basically 3 xi square 1 3. Not able to take the inverse transformation. Means that x comma y to s comma xi transformation was not 1 1. It means what was our equation? 0. This at p, that is xi comma 0, 3 xi square del u over del y, and 1 at p is 1. And similarly 1. It is simply 1 plus del y over del s at s equals to 0 and x equals to xi is simply 3 xi square del u over del y is equals to derivative of this u naught, that is equals to 1 here with respect to xi, and since it is a constant it will be simply 0. It means if you write the matrix A augmented B, A is 1 exactly. So rank of this matrix is 1. And what will be the rank of the augmented matrix? What will be the rank of the augmented matrix? Is it 1? No, no solution.
Rahul, should we start?
Yes, ma'am.
Okay. So let me first introduce to our next speaker. So our next speaker is Dr. Mukesh Kumar, and he's an associate professor in MNNIT Allahabad. And sir has completed his master's and PhD from IIT Roorkee.
Right now, first of all, I want to congratulate to organize such a nice workshop to Dr. Similarity transformation method, epsilon tau xyt plus order of epsilon square, phi xyt plus coefficient of order of epsilon square, both side leads to the first order PD satisfied by phi xt. That's the equation is the only theta and here uxx, uxt, utt, ux, our equation 1.13. So as we the requirement of the method, these two indeed earlier explained also from some little bit lengthy calculation. So I have directly written here eta x, eta t, eta xx, eta tt, eta xt, and eta xx. Previous one was first order infinitesimal. Here it is second order infinitesimals. So this is the brief description of the matter. Now I want to take the example so that you can understand how the equation can be solved. In fact, non-linear partial differential equation can be solved in the exact form along with in the form of analyticity as well as the different various type of the function involved in the solution. So here I have considered a 2 plus 1 dimensional extended shallow water wave equation is given by equation 2.1, as 2.1 is uyt plus uyt means del square u upon del y del t plus uxxxy minus 3uxxuy minus 3uxuxy plus a times uxy is equal to 0. Here a is any constant, u is the dependent variable, xy xyt are independent variable. So ultimately this is the fifth order, maybe 1, 2, 3, fourth order partial differential equation and highly non-linear. Here uxx and ux term are there. We are calling it 2 plus 1. Why we call 2 plus 1 here? 2 plus 1 means in the independent variable, 2 independent variable is xy and 1 is denoted from the variable t. That's why this is the fourth order non-linear partial differential equation with 1 dependent variable and 3 independent variable. 3 means 2 plus 1. We will denote generally space variable here 2 and last one that is for instant time variable. So where uxyt is the free surface displacement from the equilibrium level of an inviscid compressible fluid with horizontal distance x and vertical distance y from an arbitrary origin at time t. It describes a nonlinear wave propagation on the surface of shallow water wave. Equation 2 were first derived by using the idea of weak-Lax pair. Basically, weak-Lax pair is another method that is also little bit analogous to the similarity transformation method. So here we are not concerned for weak-Lax pair method. Now the new exact solution of 2 plus 1 dimensional extended shallow water wave system have been found using similarity transformation method. The extended shallow water wave system has extensive physical background. Exact solutions are obtained under some parametric restrictions. Graphical value of the solution are also taken. Appropriate choice of arbitrary constant involved in the solutions. So here we will solve this nonlinear partial differential equation with the help of similarity transformation method. So consider one parameter group of transformation. Here we are changing xyt into the another system x star y star t star u star as usual notation as we have described in the method, where epsilon is a small parameter. So after proper calculation we can find out the infinitesimal generator. Here xi is equal to 1 by 3 g1 bar tx plus g2 t, eta is equal to sy, tau is equal to g1 t, and phi is equal to minus u by 3 g1 bar t minus x square by 18 g1 double bar t minus x by 3 g2 bar t plus g3 t plus 2 by 9 ax g1 bar t. Here xi, eta, tau and phi are the infinitesimal, g1, g2 are the arbitrary function of t, h is the arbitrary function of y, and these infinitesimal can be calculated by the proper calculation, or as well as now right now there is a facility to find out these infinitesimal with the help of the Maple software also. Now characteristic equation is given by, as we have got the invariant surface, after invariant surface condition we can find out dx dy dt du as equation 2.4, dx xi dy upon tau, as we have got xi, eta, tau and phi corresponding to x, y, t and u. So here dx corresponding to this one xi, dy upon sy, dt upon g1 t and du upon this one. Now this equation is nothing but the first order form of the Lagrange as we have solved the Lagrange equation method. So similarly, we are solving here, and here we have to find out, after solving the equation 2.4, some similarity variable as well as similarity functions. So once we consider the term dx and dt here, and we are taking here g2 in terms of the function g1t, so we can get at dx by dt is equal to something, and ultimately there may be x plus c upon g1 to the power 1 by 3 is a constant, as a times x minus c by 3 minus x plus c square g1 bar upon 18 g1 g1 bar plus uxy upon g1 bar 1 by 3. So here uxy, this is called similarity function u, capital U, and u is the function of capital X and capital Y. So ultimately you can see, just I am going to reverse. Here we want to solve this equation 2.1 u. So now we are getting the form of this u given by this equation 2.5. So once we put this small u, that is expression of small u given by 2.5, into the equation 2.1, we can get the new equation in which capital U, capital X, capital Y are there. Capital U are the similarity function of variable capital X and capital Y. So once 2.5 along with capital X and capital Y put in the equation, we can get the equation 2.6. Now you can see equation you can see equation 2.1 in which there are three independent variable and one dependent. One dependent is small u and three independent x by t. Right now in equation 2.6 you are getting one dependent variable, that is capital U, and two independent variable, that is capital X and capital Y. So right now here we have reduced one variable during this calculation. We have got equation 2.6, and here is still a partial differential equation with one dependent and two independent. If once more we apply the similarity transformation method, again we can reduce one independent variable. So first we have to find out the infinitesimal generator as follows. These are given: xi cap, eta cap, phi cap, along with arbitrary constant b1, b2, b3 and b4. So where b1, b2, b3, b4 are the arbitrary constant, and on the proper restrictions of b1, b2, b3, we can find out, or we can reduce that equation into the one less independent variable equation as follows. Suppose we are not first taking b2 is equal to 0, means b2 not equal to 0. So dx upon this, dy upon this, du upon this, dx upon xi cap, dy upon eta cap, and du upon phi cap, where capital B1, B2, B3 are adjustable by these constant as capital B1, capital B2, capital B3 belong with to small b1, b2, b3. Then the similarity form of capital U is given by equation 2.7. When once we solve by du dx, we can find out 2.7. Here in arbitrary constant we have put the function u1 of x1. So here u1 is again similarity function of the similarity variable x1, and x1 can be obtained as x plus 3v1 upon y plus v2 to the power 1 by 3, and this x1 can be obtained by solving these two equations. Dx upon equation 2.7, we are reducing. One is the independent variable, only one dependent and one independent, that's why obviously the equation is reduced into the ordinary differential equation as equation number 2.8. Still the equation 2.8 is 4. After first order, you can solve anyhow by some proper assumption or by some linear or non-linear. So at that stage, you can solve the equation by some adjustment. By chance, this equation is obtained as a particular solution of this solution that is very exactly analytical as well as satisfy the equation is obtainable here. Now, once can be solved exactly without, you can see the solution in the form of 3v1 whole square v1 to the power 1 by 3 y plus b2 power 1 by 3. Capital Y is nothing but dy upon h minus dt upon g1. Here the important in the form of the function, the solution in the arbitrary function. Just take a look what was our original equation. You can see the original equation is 2.11, where still g1 is an arbitrary function. So this matter is analogous to little bit analytical solution as we got the solution linear. If we are getting the linear partial differential equation, so we will get the solution of partial differential equation in any arbitrary. This matrix also provide the solution A, C, B1, B2, B3, these all are arbitrary constant is given here and capital Y in the form of dy upon h minus dt upon g1. So if you